right, so we are going to wrap up this rather long section here, section 4.4, on something called the second derivative test. Now, this is not to be confused with the process that we were doing previously. Scrolling back up here. So sometimes this process right here that we were doing when we find where the second derivative is equal to 0 or doesn't exist, and then we do the sign analysis, that all feels so analogous to what we do on the first derivative, and we kind of call that the first derivative test, that sometimes students mistakenly think that this process is called the second derivative test, and it's not. It's just our test for, concavity and inflection points. Doesn't have a catchy name. So what is the second derivative test then when we refer to this? This is going to be an alternative to the sign analysis on the first derivative, to determine extrema. So this is for, again, now we're kind of going back. This is for determining maxes and mins. All right, so what are we going to do? So we're going to first start by finding our critical points. So we're going to look for your critical numbers. So of course that means where f prime is equal to 0 does not exist. So we start the same way. Now, as we get into this, again, be careful here, the notation on this. So the f primes look pretty good, but it's these double primes that you need to make a little more significant here. So this is also a double prime here and a double prime there. All right, so we're going to take these critical points and then we're going to sub them into the second derivative. And if you get a negative result, that means you're at the location of a max. So how I like to encourage students to think about it is that you know what it means for the second derivative to be negative, and that means you're in an interval that's concave down. So if you're kind of thinking to yourself, for example, if I'm at a point of horizontal tangency, let's say here at C, then if I'm in a region that's concave down, I have to be at a max. And then the kind of reverse of that, again, if I have found a critical point, let's say here where f prime is equal to 0, and this point, let's call it C, is in a region then that is concave up, that tells me I'm at a min. So those are the things I want you to kind of think about as you're reasoning through this second derivative test. We're going to look at an example, but if, it's just worth noting, if when you sub into the second derivative, if you get 0 or it doesn't exist, then you don't get any information from this test, and you would go back and take a look at maybe what's going on with like the first derivative test. So let's take a look at an example. So suppose we have f of x equals sine of x minus 1/2 cosine of 2x. So again, we're finding extrema here, maxes and mins, but we're going to use this test to verify if possible. All right, so first, finding our extrema means finding the critical points. So the first thing we're looking for is our f prime. Derivative of sine of x, of course, is cosine of x, minus 1/2 gets carried along. Derivative of cosine is the opposite, so that'll change to addition, of sine of 2x. But then by chain rule, we would have times the derivative of the inside, so times a 2, and of course that would reduce with our 1/2. All right, so what do we have here for our f prime? We have cosine of x plus sine of 2x. Now, we're looking for where f prime is equal to 0, or potentially where f prime does not exist. But in this situation, sine and cosine are defined everywhere, so we're not going to have anything to concern ourselves with in that area. All right, so what are things that we learned in trig to solve a trig equation? Maybe putting everything in terms of sine and cosine, well, we're already there. If this was just sine of x and cosine of x, maybe I would be looking for where sine of x equals minus cosine of x. And then you're kind of talking about the same angle, the same x. But that's not what we have here. We have a sine of 2x. So this is where we want to use, and you might have to reference your trig identities, and there is that formula sheet that I've given you. Sine of 2x, we have a nice trig identity. And maybe you have to reference it, at least hopefully you know that this doesn't just become 2 times sine of x, that there is an identity to kind of look up here. and that identity is 2 sine x cosine x. So referring to that identity, we now have that f prime is equal to cosine of x plus 2 sine x cosine x, and we're looking for where that is equal to 0. Well, that now looks a whole lot better because now we can factor out the cosine of x, leaving us with 1 times the quantity of 1 plus 2 sine of x. Now we have a product equal to 0, so we can look for where each of our factors are equal to 0. So looking for where cosine of x is equal to 0, and then subtracting 1, looking for where 2 sine of x is equal to negative 1, and then dividing by 2, looking for where sine of x is equal to negative 1/2. All right, well, cosine is equal to 0. Cosine of x is equal to 0 at x equals pi over 2, and then at 3 pi over 2, but we're really just on the interval from 0 to 2, or I'm sorry, just 0 to pi here. So really, I guess I only want that first one, just the pi over 2. And then where is sine equal to negative 1/2? So where the y-coordinate is negative, we're actually going to be out of the domain for this problem. We're down there in quadrants 3 and 4. And so, these values, if we were on the interval from 0 to 2 pi, we would be looking at the values at 7 pi over 6 and at 11 pi over 6. But I'll just kind of write, these are not in our domain from 0 to pi, so we're just not going to use those. Otherwise, we definitely would be. And then same thing here with the 3 pi over 2. This is just, once again, not in our interval from 0 to pi. All right, so we just have one value here that we're interested in, which is at pi over 2. All right, so now we want to try to use the second derivative test. So the second derivative test says, well, first, not surprisingly, we need the second derivative. So f double prime. So I'm going to work off of kind of our first form we had up here of f prime. You could work with the second one. I think I'd just rather do a chain rule on the second term than do a product rule, but it's up to you. So derivative of cosine of x is minus sine of x. Derivative of sine of 2x is cosine of 2x, and then by chain rule times that 2. And so now what we do with our second derivative test, so this is, I'll even write this out, by second derivative test. We are subbing in, we have this point of horizontal tangency, our critical point there at x equals pi over 2. And now we are subbing that pi over 2 into the second derivative. So what happens when we sub this in? All right, so we have negative sine at pi over 2, and then plus 2 times cosine of 2 times the pi over 2. And of course, those 2's would reduce. All right, so our sine at pi over 2, that's just 1, but we have the minus in front. And then your cosine over at pi is negative 1. So you're going to have, looks like we're going to end up with negative 3. But I don't even really care that it's negative 3. I really just care that I get a negative. So I'm not even going to write the answer of the negative 3. I don't want us to think that negative 3 is going to, sometimes students confuse that with being the y-coordinate or something, and that's not the case here. So what I want you to think about is this. You have just discovered that at this point of horizontal tangency, at x equals pi over 2, that you're in a region that the second derivative is negative. And where the second derivative is negative means you are concave down. So if you already knew you were at a point of horizontal tangency, and now you know that that is in an interval that is concave down, that then tells you that you have a local maximum at pi over 2. Now, if you want to know what the y-coordinate is, that always requires us to go back to the original function. So if you ever want to know actually what is that value, well, that would require us to go back to the original function. So we would have f of pi over 2, which is our sine at pi over 2, which would have been 1, and then minus 1/2 times the cosine at 2 times pi over 2, so the 2's would reduce. So cosine at pi would have been -1, and so this would have ended up 1 plus 1/2, so this would have been 1.5 or 1.5. So if you actually want the y-coordinates, you got to sub that back into the original. So this would be our conclusion by second derivative test. So that second derivative, it's this test, it's this alternative to sign analysis and discovering, oh, look, I was increasing and then I was decreasing, so I had to be at a max. So this is sort of an alternative to that. So there'll be some questions in the homework. I like to use this a lot of times when we get to some optimization problems later in the chapter. I find it to be sometimes a quick test to use, so you may see it as we move forward a little bit as well. All right, so this wraps up section 4.4.